Page 198, question number 1, review of chapter 5.4. A system of two charges has a positive potential energy. What does this mean in terms of the charge on the two charges? Well, if we have empty space, and we take from infinity and put a positive charge in the middle, it would require no work because there's no force along the way. There's no repulsion force, there's no attraction force. Now, so it took no energy to put one charge in there. But to bring a second charge in there, it's about two charges. To bring a second charge in, what does it mean that it'll have a positive potential energy? The energy will be positive. So the work is going to be the change in potential energy. And they're saying a positive, so there's going to be positive work, it will require work. So it'd be kind of like bringing in a positive charge. If you brought that charge in from infinity, it would require a force, and that potential energy is going to equal K Q over R. And if we have the same charges, both positive, then this potential energy will be positive. And if they're both negative, this potential energy will still be both positive. So what does it mean in terms of the charges on the charge on the two charges? They're going to be the same. Question 2 on page 198, chapter 5.4, review questions, states, a tiny plastic sphere is midway between the two metal plates, which are 0.05 meters apart. When the battery is connected to the plates, the sphere experiences an electric force of 1.2 times 10 to the negative 3 newtons. How much work is needed to move the charge from one plate to another? So, there are two plates here. And there's an object in the middle, and it's experiencing a force and there's a separation distance between these two plates of 0.05 meters. And this force is 1.2 times 10 to the negative 3 newtons. So how much work is it going to needed to move? Now normally when we're pushing a force, it's in a radial field, meaning around a point, and the force changes as an inverse square. So if we move an object around, we can't just use easily the work is the force times the distance, because if we're going to use this, then that force has to be constant throughout that distance. But in between plates, the force is constant. It's a constant E field between the plates. The E field is linear, not radial. And if the E field is linear, then the force is constant. So then we can just quickly come up with the formula that the work is going to equal the force times the distance, plugging these two numbers in of 1.2 times 10 to the negative 3 and 0.05, we come up with 1.2 e to the negative 3 times the distance of 0.05 meters, and it's 6 times 10 to the negative 5. So 6 times 10 to the negative 5 joules. Now, will that work be positive or negative? It depends on which way you're moving it, against the force or with the force. And how much work? So I'll just leave it as plus or minus, depending on which way you're moving it, because it doesn't clear. Another trick is saying that it's placed midway between it. That doesn't really matter. The force is going to be the constant no matter where we are in there. That's how you do that question. With question number 2. Now we're doing question number 3 on page 198. That's from chapter 5.4 on electrostatics. What is the change in potential energy of a particle of charge q that is brought from a distance of 4r to a distance of 2r from the charge of negative q? So there's a charge of negative q over here, and we're going to leave that fixed. and we're bringing a charge of Q that is 4r away to a new location. I'll just put it by dotted. That's the new location. It's 2r away. What is the change in potential energy? Well, change in potential energy is the potential energy final minus the potential energy initial, and that's going to equal KQQ over final is 2r, and it'll be KQQ over the initial, which was 4r, but one of these Q's is negative. Okay, I'm going to gather like terms and pull them all out. I will get KQQ over r, and we'll bring out a 2 as well. And that will leave us now. Let's get the signs happening here. This is going to be the positive one. There's 2 negatives. So this will be 1/2. And this will be just -1. So 1/2 minus 1 is a -1/2. So this is going to be -1/2 of this KQQ over 2r. So the answer will be, and I'll do it in black over in here, it's going to be negative KQQ over 4r. Or if you want Q squared, because it is the same charge, but just that's the value. That'll be the change in potential energy. And it wants to go there, so it is kind of like going downhill. It's a loss of potential energy, so that looks right. Number 4 on page 198. How much work is needed to bring a 5 microcoulomb point charge from infinity to a point 2 meters away from a 25 microcoulomb charge? So we're ending up, the final has a 25 microcoulomb charge and a 5 microcoulomb charge, and the distance away is 2 meters, and that's the final. Initial is way out here at infinity. The 5 microcoulomb charge is way out here at infinity. So at infinity, the potential energy is going to be 0, because the definition of this formula that we used and how we derived it is that when we have a separation distance of infinity, then the potential energy is set to be 0. That's our 0 point for our potential energy. So the initial is 0. So the final minus the initial will be the work. The work is the change in potential energy, which is potential energy final minus potential energy initial, and that is just 0 by definition. So the work is just going to be the potential energy final. So work is going to equal KQQ over R. That's our formula. We put in the K and the 2 Q's of 5 times 10 to the negative 6 and 25 times 10 to the negative 6 all over 2. We plug that into our calculator. Pardon me. K is 9e to the 9th times 5e to the negative 6 times 25e to the negative 6 divided by 2, and that will be our work, how much work it requires. So the work will be equal to 0.565 joules. It will be positive. First of all, we did put both positive numbers in there. We trust the formula, but they don't want to get together. So by pushing them closer together, because they are like charges and they repel, it will require work. And this is different than the answer in the back of the book, at least in this year's edition of the video of the book. Number 5 on page 198. What is the electric potential energy of an electron relative to infinity when it's 7.5 times 10 to the negative 11th meters away from a proton? So we have a proton electron, and its distance is 7.5 times 10 to the negative 11 meters. The potential energy at infinity is 0. So the final is the potential energy. It would be K Q over R. And the Q's will be the elementary charge. One will be negative because the electron is negative. So this is going to be 9 times 10 to the 9th. The elementary charge is 1.6 times 10 to the negative 19th. And there's two of the elementary charges, so I'll just square it. But I'll make sure that the negative does come out. That is the electron. One of the negatives, the negative of the electron will come out. And the separation distance is 7.5 times 10 to the negative 11th. So in the calculator, it's going to be 9e to the 9th times 1.6 e to the negative 19th squared divided by 7.5 e to the negative 11th. And to make sure I put the 11 in there, and boom. So the energy there, the potential energy will be a negative 3.072 times 10 to the negative 18th joules. So what does that mean? It's negative, so it'll require that much energy, positive 3.072 times 10 to the negative 18th joules to ionize this proton. Because right now we've got the old hydrogen atom. Anyhow, thank you very much. That's the answer. So this is number 6 on page 198. As shown below, we're taking a 4.5 times 10 to the negative 7 Coulomb charge, and it's initially at 7 meters away from this fixed charge of 6 times 10 to the negative 6 coulombs. And we're trying to figure out that we're bringing it 1.5 meters closer. So what will be the amount of work required to do it? Well, it doesn't want to go that way because it's a repulsion force, so it will require positive work. We have to just take the potential energy final minus the potential energy initial. So the potential energy final is going to equal KQQ over R, and that's going to be 9 times 10 to the 9th. The two charges of 4.5 times 10 to the negative 7th, and the other charge of 6 times 10 to the negative 6 coulombs. And the final separation distance, this distance here, is going to be 5.5 meters. So we'll go 5.5 meters down there, and that'll get us the potential energy final. And we do this all again, except we change that number there to 7 because that's how far away it was to begin with. That's the initial. And then we subtract those two values. So let's just plug it into the calculator here. That's going to be 9 e to the 9th times 4.5 e to the negative 7th times 6 e to the negative 6. That's the numerator. And then I'll divide that by 5.5. And I get the potential energy final is this number, 0.004418. And the potential energy initial by the same work, except the new number of using 7 here. So this was the numerator. And I divide that by 7, and that'll give me my initial potential energy. Now I just have to subtract that, take my final minus the initial. So take my final, subtract the initial, and I get the change in potential energy is going to be 9.467 times 10 to the negative 4 joules. And that will be how much work it is, because that's the change in potential energy.